Thanks, everyone. Okay, thanks everyone for joining. It's an unusual time to try to, bridge the time interval between the UK and Berkeley. Thanks, Jaime, for agreeing to give a rather late talk, late your time of day, but there's a fair crowd and more joining, and why don't you go ahead. The topic is probing jet energy redistribution and broadening in heavy ion collisions with the Alice detector, the LHC. Go ahead, Jaime.
Yeah, thanks, Peter, and thanks a lot for the invite. Actually, to share some of these recent measurements that I've been involved in, jet measurements with Alice at the LHC, and so I think you'll all be kind of familiar with QCD and the kind of background here, but I wanted to give a very brief background as to what we're measuring and why we're measuring it. And so the first kind of question that we can ask when we look at the different phases of nuclear matter is what is the structure of nuclear matter, of QCD matter, over a range of energies and densities. So we can kind of do this by trying to map out the phase diagram of nuclear matter, which I show here as a function of the baryon chemical potential or the baryon density and the temperature of nuclear matter. So kind of at cold temperatures, we have kind of nuclear matter as it exists around us. As we start to kind of heat up nuclear matter, it can break up and form a hadron gas. But as we keep heating it up at very high temperatures, we get this kind of phase transition to a deconfined state of quarks and gluons. So this is known as the Quark-Gluon Plasma. And at low baryon density, we kind of expect this kind of smooth crossover at around 160 MeV. And so experimentally, we can create this phase of matter using ultra-relativistic heavy ion collisions. And at the LHC, is where the Alice experiment is, for 1 month a year, the LHC collides lead ions in order to study the Quark-Gluon plasma. So this is kind of my one-page summary of the Quark-Gluon plasma in a nutshell. So over kind of the 20, 30 years that we've been experimentally studying the Quark-Gluon plasma, we've determined that its kind of long-distance structure, it acts like a strongly coupled liquid with very low viscosity. And kind of roughly comparing the viscosity over entropy density, we get a value for the Quark-Gluon plasma created in heavy ion collisions much lower than any liquid that we know of, and very close to kind of the lower bound for a strongly coupled gauge theory. So this has led to it becoming known as the perfect liquid. So it's kind of strongly coupled, but we know that it's formed from kind of weakly interacting constituents, quarks and gluons. So we kind of also want to know kind of its short distance structure. So is it kind of created from free quarks and gluons, or their kind of complex bound states? And really the kind of constituent degrees of freedom aren't yet fully established experimentally. So kind of a big question, and one that I'll kind of come back to throughout this talk, is what is the structure of the Quark-Gluon plasma as a function of the resolution scale? So I'd like to talk about how we can probe the Quark-Gluon plasma in heavy ion collisions. So this is kind of a simulation of a heavy ion collision where we have kind of these Lorentz contracted disks that collide, form this Quark-Gluon plasma, which then rapidly expands, cooling and eventually forming hadrons, which we measure in our detector. This happens over really a very short timescale of the order of 10 to the minus 23 seconds. And to probe this state of matter, we kind of have many tools in our toolbox. So we measure this kind of final state distribution of hadrons. We can look at, for example, its kind of hydrodynamic flow by measuring the kind of momentum distribution of hadrons at the end. We can measure the hadron chemistry and kinematics, which sort of tell us about sort of its point at hadronization. We can measure kind of electromagnetic radiation, which can tell us, and also quark-gluon dissociation regeneration, which can tell us, for example, about its temperature. Or we can measure we can aim to measure sort of partonic interactions within the quark-gluon plasma, which is what I want to talk about today. And to do this, we can use heavy quarks, or in the case of this talk, jets. So we know that a jet in kind of collider physics, in any collider experiment, is kind of comes from the evolution of a hard parton produced in a hard scattering process. So a quark or a gluon that sort of evolves, radiates gluons, and through this parton shower is experimentally measured as a collimated spray of hadrons. So could you actually turn your speaker off? I'm not sure if that's in the room.
It's us.
Want me to mute it?
Mute us, yeah.
Okay.
Is that okay? Okay, thank you. Thanks. Okay, so yeah, this is kind of a jet in collider physics in vacuum. So when we go to heavy ion collisions, we get jets that are produced that undergo kind of interactions with the quark-gluon plasma via kind of inelastic medium-induced gluon radiation or elastic processes over the full parton shower. So this is an effect known as jet quenching. And by measuring jets in heavy ion collisions, we aim to kind of really probe the quark-gluon plasma at multiple scales. So the bread and butter measurement in heavy ion collisions is this nuclear modification factor, RAA, which is the yield of something in lead-lead over that in proton-proton collisions, scaled by the average number of binary nucleon-nucleon collisions in these lead-lead collisions, which kind of asks how different is the production of something in heavy ion collisions compared to the same number of independent proton-proton collisions. And we can look at this RAA for jets, which are shown here for LHC experiments, Atlas, CMS, and Alice, as well as STAR at RIC, where we see this significant suppression, RAA less than 1, which is interpreted as jets losing energy as they traverse the quark-gluon plasma. So this is this kind of quenching effect. So this is kind of what we measure in experiment. We want to kind of aim to model jet quenching in as much detail as we can, and there's a number of techniques that are used to do this theoretically. I just showed kind of limiting cases here. So at the hard end of the scale, we can use a perturbative QCD approach where the jet medium interaction is described by scattering matrix elements, and we also include additional medium-induced radiation. And at the kind of softer end of the scale, one kind of interesting way to describe soft jet medium interactions non-perturbatively is through this kind of gauge gravity duality, ADS-CFT, where the kind of strongly coupled plasma is kind of mapped to a weakly coupled kind of string theoretical quantum gravity description of strongly coupled field theories. So nowadays, these kind of techniques are implemented in Monte Carlo generators, which are really kind of detailed simulations of all aspects of the collisions from its initial state, the medium fluid dynamics, the jet evolution, all the way up to its to kind of the partonic hadronization. So so these are kind of the background of jet measurements in general in heavy ion collisions. So so why do we want to measure jets? And I kind of want to make a broader point here of how can we probe the structure of any matter, any state of matter. Okay. And we're physicists, and we like scattering experiments to do this. So these are some scattering experiments in sports. So on the left, Liverpool beating Man City, and here the kind of whether the ball scatters off the goalkeeper or goes into the goal affects the outcome of the game. I think this is closer to home in Berkeley, the University of California baseball team, where depending on the kind of the scattering probability of the ball to the bat, also the scattering angle depends on whether you score a home run or you're out. So this is kind of my bad sporting analogy. Looking to kind of to real physics experiments, we can take the Rutherford scattering experiment as an example, where Rutherford, just down the road from here in Manchester, by firing a alpha particle at a gold foil and measuring the scattering angle of this particle, in particular, measuring the occasional large angle scatters of this alpha particle occurred. Through this experiment, determined that the atomic structure consisted of a kind of concentrated point of positively charged protons and neutrons, where all the mass was contained, or most of the mass was contained, surrounded by negatively charged electrons. So really kind of out of this experiment, all of nuclear physics, particle physics, and really our understanding of the fundamental building blocks of our universe came from this. Another example is kind of deep inelastic scattering, so at SLAC and then later at HERA, for example, by firing electron beams at a target and measuring the scattered electrons and recoiling hadrons. It was determined that hadrons, protons, neutrons consisted of constituent particles, quarks. And also interestingly, it was determined that as we probe kind of hadrons at different resolution scales, a kind of more complex picture emerges of the structure of hadrons. So the question is whether we can perform this kind of similar scattering experiment in the Quark-Gluon plasma. So kind of Rutherford-like scattering experiment be performed. So this will kind of allow us to constrain transport properties of the Quark-Gluon plasma, and also interestingly may allow to determine the quasi-particle structure of the Quark-Gluon plasma, and also study how a strongly coupled liquid emerges from the constituent degrees of freedom. So ideally, we'd kind of create this Quark-Gluon plasma and take it to kind of an electron beam and really kind of study this in great detail. But this Quark-Gluon plasma sort of disintegrates after a fraction of a second. But jets are suited for this task. So we produce jets in these collisions, and then they experience the full evolution of the system. So this is kind of a more complex task than these kind of these other examples that I've given. But this is kind of one of the main goals of kind of jet measurements in heavy ion collisions. To do this, really comparing heavy ion measurements to a vacuum reference in proton-proton collisions is crucial. And sort of one of the main proposed methods to perform this kind of these sort of scattering experiments are measuring the transverse broadening of a dijet system, so measuring its acoplanarity in heavy ion collisions. So this is actually an old idea, and yeah, I realized recently, actually, from Peter, that this was one of the first proposed signatures of the Quark-Gluon Plasma formation, even before the Quark-Gluon Plasma was kind of confirmed in experiment. But it's a very challenging measurement, and yeah, we're kind of just getting around to these kind of detailed measurements now. And so there's two regions of interest that I would like to talk about. So looking at this kind of dijet system, there's kind of this small KT region and this large KT measurement. So so transverse broadening can occur due to kind of multiple soft scattering in this small KT region, which can be quantified by jet transport coefficient Q hat. Which is the average transverse momentum squared gained per unit path length traveled of a jet. So jet acoplanarity provides a direct probe of Q hat. At the moment, if we look at the value of Q hat as a function of temperature, we see that it's not very well constrained. And this kind of measurement can give us real insight into Q hat. In this kind of large angle scattered region, we expect kind of in the strong coupling limit, the probability of a parton to obtain momentum KT is Gaussian, as shown here, whereas scatters off weakly interacting quasi-particles it's been determined would look more like a power law distribution. So we expect that at kind of large enough KT, these kind of jet scatterings will be dominated by these kind of large angle weakly interacting scatters. And so the question is, can hard scattering be discovered in the tails of the jet acoplanarity distribution? Okay. So far, jet acoplanarity measurements have been made. So by CMS, kind of measuring gamma jet correlations, also by Alice using run1 data and STAR. And so far, there's no evidence for Quark-Gluon Plasma induced acoplanarity so far, which means that the shapes of these distributions are consistent with kind of a proton-proton vacuum reference. However, theory indicates that low PT jets should be most sensitive to these broadening effects. So this kind of motivates pushing this measurement down to as low transverse momentum as we can. So kind of finally on this kind of motivation, I want to mention what happens to the medium when a parton propagates it. So we know that jets lose energy due to the interaction with the medium, but of course energy is conserved. So that must mean that the medium is modified by jets. And we expect kind of a number of effects that a jet propagating through the medium would happen to the medium. So we expect wake-like effects. And by measuring this kind of this wake, seeing how the medium responds, we can aim to sort of measure properties of the Quark-Gluon plasma, right? If a duck crosses a pond, we can look at the sort of wake to determine properties of the liquid that the duck's traveling through. And it's the same with the Quark-Gluon Plasma, right? We can try to determine its equation of state through these measurements. These wake effects may also affect kind of interpretation of jet measurement. So can we separate the medium from the jet? Or how do these medium effects affect these jet measurements? Okay, and then finally, kind of dealing with background in heavy ion collisions. So in proton-proton collisions, we get kind of very few charged particles that are produced, whereas in central lead-lead collisions, we get a huge number produced. So these kind of event displays of Alice really show kind of how much background we have in heavy ion collisions. And this uncorrelated background, so background that doesn't come from these hard scatterings, is a major challenge for jet measurement. So what is a true jet from a hard scattering and what is from uncorrelated sources? So this is especially important for low PT measurements and larger radius jet measurements. So this talk will concentrate on a kind of statistical approach to correcting for the background. And I'll show details in a second. You can also see kind of other jet-wise approaches that that Alice has developed in these links if you're interested. But okay, so this is the background of this measurement. Really, so today I'd like to focus on these two measurements that were recently on arXiv submitted to PRC and PRL, where we probe these effects, energy redistribution, jet broadening with Alice using a hadron jet correlation measurement. So first, I just want to show some information about the experimental setup here. So you can see the Alice. So it's made with the Alice experiment, which is shown here. We use the tracking detectors, the inner tracking and the time projection chamber to reconstruct charge tracks. And this is done kind of selecting the most central collisions using the V0 detector. Using data samples from run 2, so a proton-proton data sample consisting of around 1 billion minimum bias events, and a lead-lead sample consisting of around 90 million central events. So these charged particles are kind of clustered into jets, and using the anti-KT jet algorithm, and the analysis is done for 3 separate jet radii. So kind of narrow jets are equals 0.2 jets, and wider jets are equals 0.5 jets. And so the analysis technique, the procedure, I'd like to just go into a bit of detail here. So we're measuring hadron jet correlation. So we first select events based on the presence of a high PT, what we call trigger hadron. And so the idea here is that we kind of select events based on this kind of hard process. By selecting a hadron trigger, we have kind of a clean trigger, so there's no kind of background correction necessary. And also by selecting kind of high PT hadrons, we select events where the hadron is has kind of a bias towards the surface. Which means that the jet preferentially kind of travels through a larger path of the medium. So once we select our events, we then do jet reconstruction on these events, and we count the jets recoiling from the trigger hadron as a function of both the opening angle of the jet relative to the trigger axis, as well as the transverse momentum of the recoiling jet. And then we define this observable, which is the what we call the trigger normalized yield of charged particle jets recoiling from these high PT trigger hadrons. And the idea here is that this observable is perturbatively calculable, so it's the ratio between the high PT hadron and jet reduction cross sections. And the analysis is done in a semi-inclusive way, so events are selected purely based on the presence of this high PT trigger, and we count all of the recoil jets in the defined acceptance, which is kind of crucial for the next step of the analysis, where the uncorrelated background is subtracted by constructing this delta recoil observable, which is the yield difference between two of these trigger normalized recoil jet distributions in what we call a signal trigger track class, which is kind of trigger tracks with high transverse momentum, subtracting the reference distribution in a reference class, which corresponds to triggers in a lower transverse momentum region, where the reference distribution is scaled for normalization constant extracted from data to ensure that the uncorrelated background component is consistent between the two distributions. And the idea here is that the uncorrelated background component of these distributions is by definition kind of uncorrelated with the trigger track PT. So this subtraction provides data-driven subtraction really of all uncorrelated background. So this includes kind of removing multi-parton interactions, which improves sensitivity to these large angle scattering effects, and also allows for the measurement of the jet spectrum over the kind of really the full PT range, which allows for low PT large R measurements. And reminding you that kind of these low PT, low PT jets are where these effects are expected to show up. So we can take a look at how these distributions look in data. So I show the 2D recoil jet, trigger normalized recoil jet distributions in the signal trigger track class. So here we take the signal classes between 20 to 50 GeV, the reference classes between 5 to 7 GeV. And we just focus on the kind of back-to-back region, so around delta phi equals pi here, where we see in both proton-proton and lead-lead collisions this kind of broad structure, which are the jets recoiling from this trigger hadron. So it's easier to kind of visualize this if we take projections onto the PT and the delta phi axes, which I show here for the signal class in red, the reference class in blue, and then this delta recoil, which is the difference between these two classes in black. And yeah, it's interesting to point out here that these kind of two regions where at high PT, the signal jets dominate, delta recoil kind of becomes close to the signal distribution. As we go to lower PT, the distributions start to match, and in this lowest PT region, we see this really remarkable match of the distributions over many orders of magnitude. So this kind of confirms that this is the region where the uncorrelated background is really dominating in this measurement, and this subtraction completely removes this. So these are the raw distributions. The the distributions are corrected, unfolded for both detector effects and also the residual background fluctuations in both proton-proton and lead-lead collisions. We correct in one dimension when we measure this delta equal as a function of PT, taking into account that there's kind of minimal delta phi smearing. When we make this measurement as a function of delta phi in different PT intervals, we unfold in 2 dimensions, the jet PT and delta phi. And all correction steps are fully validated via a closure test where we run this full analysis chain on Pythia jets that are embedded into a lead-lead background, where we can really kind of compare the unfolded result to what we expect from kind of the truth. And then I list the systematic uncertainty sources that we consider here. I can just mention in proton-proton collisions, the dominant uncertainty sources are due to tracking, and in lead-lead due to the unfolding. Okay, so that brings me to the results sections. And here I'll kind of show this in 2 parts. So I'll show first the delta recoil measurement as a function of the jet transverse momentum, where we project this 2D distribution onto the jet PT axis in the peak of this kind of in this kind of back-to-back region, close to delta phi is equal to pi. So first, here we can see the fully corrected delta recoil distributions as a function of the jet PT in both proton-proton and lead-lead collisions. And it's nice to kind of note that the delta recoil distributions are measured down to a transverse momentum of around 7 GeV in both proton-proton and lead-lead collisions. So this is really among the lowest jet PT measurements in lead-lead collisions at the LHC, which this technique really allows for. We see the results separately for our kind of narrow jets, 0.2 up to our wider jets of R equals 0.5. And we already see some differences in these lead-lead and proton-proton distributions, which we can kind of probe in a bit more detail by taking the ratio, which I show here. So this is the what we call the IAA, which is the ratio of the delta recoil in lead-lead over that in PP. So this is the IAA for R equals 0.2 jets, and we see some kind of interesting, let's say, structures here. So in this kind of mid-PT region, we see a suppression, so an IAA less than 1. So the usual interpretation of this is jet energy loss due to interaction with the Quark-Gluon Plasma. As we go to higher transverse momentum, we see this rising trend. And this I'll show in a bit more detail in a sec, but this we interpret as an interplay between that hadron and jet energy loss. So where the jet PT is kind of larger than the PT of the trigger track, we expect larger energy loss of the trigger. And yeah, so this is kind of our data. We can also kind of look to models, and here I show comparisons with Jetscape, which includes energy loss based on different models for kind of high virtuality and low virtuality jet medium interactions. Comparisons to Joule, where the medium response effects are modeled via the treatment of kind of recoils and can be switched on or off. And then also the hybrid model, which includes this kind of ADS CFT formulation for strong coupling and DGLAP jet evolution for weak coupling, where again, the medium response effects can be switched on or off. And also these kind of elastic scatterings, large angle scatterings can also be switched on or off. we see that the models in general, so in particular hybrid and Jetscape, capture this rising trend, and Jetscape also kind of captures the full evolution of the data. Joule describes the kind of low PT IAA, but kind of slightly underpredicts the data at high PT. So these are the results for narrow jets. We can go to R equals 0.4 jets here, where we see a kind of similar trend, rising trend with PT. Interestingly, at low PT, we see this significant rise. And here we can interpret this as energy recovery. So jets that perhaps lose energy at higher PT, the energy is kind of recovered at lower PT. And this rise crucially is reproduced by models that include these medium response effects. So the medium interacting with the jet, the energy transfer that can then be recovered at low PT. So this is, a really kind of, I think a first measurement of this sort of energy recovery for jets. As we go to our kind of wider jets, R equals 0.5 jets, we see instead that the IAA is consistent with no suppression over the full PT range. So this little suppression is captured by Joule, going to kind of higher PT with recalls on. So this is kind of indication of perhaps intrajet energy recovery. As we increase the cone radius, we may be recovering some of this lost energy. Although the redistribution of the energy for R equals 0.5 jets is more challenging for models, so we don't see this rise.
Actually, Jaime, can I make an additional comment here?
Yes,
so
sure.
If you would cover up all the model names and just show it to a random, physicist in the hallway, and say, the data are the red points with the boxes, and the colored lines are the models. Do the models describe the data? The answer is absolutely not. I mean, every one of these models, which are state of the art, largely fails here. So, I mean, I know you have more to show, but I would say this already indicates that much of this modeling, including the medium response, has to go back to the drawing board.
Oh,
Yes, yeah, exactly, Peter.
That's your comment.
That's my comment. What's your comment?
No, I remember a couple of weeks ago, or last week actually, and we were at the DC, we were talking about the Q hats. And the people say that Peter had a very strong comment on this. Okay.
Yeah.
Same thing. I mean, I have the same feeling. I mean, all the model doesn't. I mean, none of them actually works. And also, particularly for R equal to 5.5 and R equal to 0.4.
Well, the Jetscape worked for the other two, right?
But not this one. So.
No, that's right.
Well, Jetscape is, it's better. Maybe Jamie toggle back and forth between the different R's. This is, yeah.
I mean, here
that's
is
good enough for government work.
Good enough for government work.
But then when you go to the next slide, it doesn't work. So I mean,
go back to 0.2.
That also Jetscape works pretty well.
Yeah, I don't know.
Yeah, I mean, we're not going to tune the models here, but I think there's some fundamental discussion needs to be had about it.
Yep.
Yeah. Okay. Good. Thanks.
Thanks, Peter. Yeah. So it's a good point. So there's kind of regions where the models describe the data, but overall, there's not one model that describes the full range of data. So I wanted to give a kind of quick aside on this sort of rising trend. And so it was kind of a puzzle when we first saw this. How can we interpret IAA greater than, or well, equal to 1 or even greater to 1 at high PT for jets with a PT of around 100 GeV, given that for kind of inclusive jets, over the full PT range, yeah, from kind of down in the tens of GeV up to even the TeV range, we see significant suppression. And the answer here was kind of confirmed recently after after our papers were released by this really nice study where the surface bias of kind of triggers was looked at in more detail. So this plot shows kind of the surface bias for trigger partons in the same kind of PT range as our measurement, 20 to 50 GeV in lead-lead collisions, where we see, so this is kind of the kind of, let's say, production vertex position of these high PT triggers, where we see kind of the production is biased towards the surface of the collision, but there's still a significant population that are produced in the center, even kind of on the other side of the collision. So the triggers may still experience significant energy loss. And when we look at how this might affect the IAA, they did this nice study where, okay, they looked at this LBT model. This was done, these studies were done with LBT. So this same kind of rise, just running the model as it is. They also ran a kind of baseline model where they took the trigger from LBT, the kind of quench trigger, but then constructed jets from Pythia, so unquenched jets, to give an idea of kind of the true sort of baseline of this measurement. And due to the quenching of this trigger, which kind of affects the sort of the trigger spectrum in different, in lead-lead collisions compared to the vacuum reference, we can expect the true baseline to be kind of much larger than 1. So it kind of extends up to, okay, this is 1 here. I cut the axis off, but it extends up to kind of 3 or 4. Which means that, jets with IA greater than 1 may still be quenched. So this observable, kind of a nice point here is that it does produce it provides kind of unique sensitivity to the interplay between jet and hadron suppression, jet and hadron energy loss. One note here is that these calculations were kind of done at the parton level, so full calculations at the so this doesn't kind of exactly correspond to our measurement, but kind of full calculations at the hadron level using Jetscape are ongoing at the moment. Okay, so kind of the final results that I want to show are the results as a function of delta phi. So here we do a kind of a projection of this distribution, this 2D distribution onto the delta phi axis for various jet PT intervals. And I show here the kind of full range of data that we have. So these are the delta phi distributions for jet PT ranging from 10 to 20 GeV up to 150 GeV. Sorry, 50 to 100 GeV on the right for R equals 0.2 jets at top down to R equals 0.5 jets at the bottom. So we compare the lead-lead and PP distributions, and for the most part, we see the shapes are kind of fairly consistent between lead-lead and PP, except for the lowest PT region for R equals 0.4 and 0.5 jets, where we see this significant broadening of the delta phi distribution in lead-lead collisions with respect to proton-proton collisions. So again, we can take the ratio here. So I show the distributions here for R equals 0.4 jets, as well as the IAA in the bottom panels. And we see in this lowest PT region, this significant broadening. For R equals 0.4 jets, this amounts to 4.7 sigma deviation of IAA from kind of the, from a flat shape, okay? So this, this is sort of really interesting. It's the first time that this significant azimuthal broadening has been measured for jets. And we can kind of ask what might be the physical mechanisms behind this broadening. And just by looking at the data, we can make some interesting conclusions. So we see this sharp transition to broadening from r equals 0.2 to r equals 0.4 in the lowest jet PT region. So this shows the IAA for r equals 0.2 jets in red to r equals 0.4 and 5 in blue and green. And so we can think that this kind of sharp transition could be caused by soft radiation. So if we have kind of this diffuse radiation that is being reconstructed as a jet, the kind of yield of these jets may scale with the area of the jets, so with the square of the radius. So this kind of indicates that it could be an effect of the response of the medium or kind of soft radiation due to the jet propagation through the QGP. When we look at Molière scattering, so this kind of large angle scattering, this radius dependence wouldn't be expected. If we kind of have a platonic scattering, we'd expect to measure the jet, whether we use kind of a cone size of 0.2 or 0.5. So really just looking at the data favors the medium response to that.
Can I ask
Yes.
a question?
Yeah.
So it seems to me, I mean, so you go from 0.2 to 0.4 on the left, again, this sequence jumps. But then if you go from 0.4 to 0.5, nothing happens. That suggests to me, I mean, 0.2, 0.4 is 0.2, the difference, and they have to have different, nothing happens. That suggests to me that there's some kind of intrinsic delta phi in there. And of course, it would be nice to see an R of 0.3, right? So is that really an onset? or is that, I mean, your argument would suggest that for 0.5 it should get even larger. It doesn't. So how do you get around this?
So you mean the kind of consistency between 0.4 and 0.5?
Yeah, well, I mean, since you see such a large jump from 0.2 to 0.4, I would expect I should see about half the jump from going from 0.4 to 0.5, just by the principle of insufficient reason.
Can I suggest, so Jamie should answer, I have an answer to you.
Okay.
Jamie, go ahead.
I'll let you
You'll
answer.
defer? Okay, the data are what they are.
I take that, yeah.
We see what we see.
Yes.
We've done, n, where n is a large number of checks. We are fully confident. We're fully confident that they're, so how to understand this?
Yeah.
Well, first of all, air bars are air bars, so maybe this is, however, let's just take your observation. I see the same thing, obvious. What could it be?
Yes.
So Jamie has this first subbullet soft radiation. What do we really mean by that? So let's imagine jet quench is extreme. You've got some parton, but just turns into nothing. Turns into soft radiation, but that kind of has some scale. So how do you get into left plot? You have to have something. First of all, we've gotten rid of all uncorrelated background.
Yes.
So it's radiation that's correlated with the trigger. That's the nature of the measurement. We have soft radiation correlated with a trigger over some area. It has to integrate to 10 GeV to appear in that left plot. And so the probability, you've got a bunch of soft radiation, you've got a small cone, to get to 10 GeV is r squared less likely than 4 and 5, but maybe this also has a transverse extent by the nature of jet quenching. Perhaps it's kind of limited in.
Yeah, that's what I'm
R.
saying. It seems that there seems to be some scale sitting in
That's
there, right?
exactly right. Yeah. Okay, so your comment about 0.3 is right. We're not going to do it for this paper, next generation.
Yeah.
Jamie has more to do. But this it's not just that it's soft radiation, but this also
There
seems
is
to
some
indicate
intrinsic
some-
overall angle of this.
exactly some
Yes.
kind of finite scale. So there's
Yes.
more here than just saw.
Yep.
So the first point is which is kind of can we see Moliere scattering? Before we compare to a model, this seems inconsistent.
Right.
That's already
No,
something.
no, fair enough.
But then this may be telling us more about the medium response.
Yep.
Okay. Sorry.
Good.
Jamie, go ahead. Yeah. More here. I'm going to mute again, so you're not disturbed.
Okay.
More comments in the room? No. Okay. Comments from the internet? No.
Okay. So yeah. So okay. Yeah. As we said, these are the data that we measure. We can also look to models to interpret this measurement, and I will yeah, for the interest of time, just focus on this kind of 10 to 20 GeV bin. I showed the full kind of range of data here. But just looking at the 10 to 20 GeV bin for R equals 0.4 jets, we see that the broadening is captured if kind of medium response effects are switched on. So this broadening occurs for both Joule, which is shown in pink, and the hybrid model to a lesser extent for 0.4, but we'll see for 0.5, when these medium response effects are switched on. Whereas we see negligible broadening if the kind of Moliere scattering effects are switched on. So the hybrid model comparing blue to green or yellow to red here. Okay, so yeah, so these are kind of the model comparisons and the explanation for this broadening. We also see for 0.5 the same thing, right? So the broadening is captured if these medium response effects are switched on, while elastic scattering doesn't have this kind of broadening effect. So the model comparison kind of further confirms the picture that the measured broadening is predominantly dominated by the response of the medium to the jets. And it is kind of quite remarkable somehow that Joule describes all of the data for all jet radii for all jet PT if these medium response effects are switched on. It should, however, be caveated that as we mentioned earlier, these models don't reproduce all features of the model. Sorry, these models don't reproduce all features of the data. And one kind of example here, so this very nice measurement of inclusive jet production, inclusive jet RAA recently that Peter was also involved in, measuring the inclusive jet yield down to very low PT. We see in this kind of overlapping region, 10 to 20 GeV, let's say, that Joule with recalls on gives this kind of large jump at low PT, which isn't seen in the data. Okay, so yeah, so this is so models can be really helpful to aid interpretation, but there's still no model that kind of describes all measured observables. This is still a challenge.
So let me see.
Hold on.
Can you go one back? So
Yeah.
do I get this right? I mean, the bin where the Joule fits the delta phi is exactly the same energy range where it totally fails on the RA.
Yeah,
Right? Is that right? Is that what you're trying to tell us?
You're being unfair. Yes, exactly.
Okay,
exactly.
so okay, got it. Thank you.
So
I got the message.
So your theory friends have no idea what they do.
I got the message. Okay, thank you. Just wanted to see if I misunderstood something.
We're going backwards at high velocity here.
So may I have a question? So when compared to the model do the same background subtraction as your data did?
Yeah, so that's a good point. So Joule themselves recommend a prescription for including kind of the medium response in the jet reconstruction, but then subtracting the recoils from the jet itself. So in terms of
these are not. I have to say, these are not full event generators. Joule does not generate a whole heavy ion event. It kind of models the effect of the medium, and it basically produces a modified 50 jet. You can think of it that way. So there is no background in the event. So it comes, pre-subtracted.
Okay, so it's not an apple-to-apple comparison.
It is absolutely an apple-to-apple comparison. We remove it. I have to insist. Sorry, Jamie, I'm stealing your time here.
No worries.
Background correction, contrary to the view of many people in heavy ion field, from my perspective, background correction is entirely an experimental question. It's our responsibility to correct the background and then to compare to theoretical calculations at the level of what we call particle level, generator level. Any theory attempt to model, the complexity of a heavy ion collision and to mock up some funky, approximation of an experimental correction, which includes unfolding, which is a very subtle and complex business, and all the experimental, just bound to fail. It's just a wrong approach. So one should take the generator level from the model and compare to fully corrected data. That's the only way to make progress. Sorry for my lecture.
So
There's somebody online. Oh, he lowered the head.
Yeah, Raymond.
Yeah, I just had a quick question. Can you remind me, Jamie, is the subtraction of the recoils here done with this 4 momentum sub approach, or this newer constituent subtraction type approach?
It's done with the 4 momentum subtraction approach.
Okay, thanks.
Yeah.
I mean, I don't think it makes a big difference at the inclusive level or like kind of the full jet level, but I was just curious. Thanks.
Yeah, so this so I was kind of reading up on this new approach.
So
Okay,
I have a question here. So your left plot is and the right plot is R equal to 0.3. That's what the worker are looking for.
Yeah.
So indeed you have apple to orange comparison.
Yeah, that'll all get fixed. That's
What do you mean fixed?
be patient. It's the right one, and we're doing the other R's as well.
So the left one is R.2 and the right one is R.3, right?
Yeah, that's what.
The left one is 0.2, 0.4, 0.5, so brackets.
Okay, oh, the 0.3, very good. That's what I wanted.
That's actually a critical point. So 0.3.
You guys have to be patient. You got us. All right.
Okay, all right.
So I do have a question. So suppose your left plot for 0.3 also go up, right? Your data. So that has to be consistent with what you for the inclusive one. So one thing I kind of a little bit confusing because somehow your inclusive measurement doesn't say any kind of increase. I mean, of course, delta phi. I mean, the delta phi distribution is like a flat, right? So if you have some increase for large angle, then you would say in the inclusive.
Yeah, it's really good. Jamie, go back to the actual delta phi distributions, not the ratio.
Not the ratio.
The large, they're falling by, well, it depends which one you take, but.
I mean, the force beam, of course.
Yeah, if you're looking at the far tail, it's 10% or less of the total yield. So we're looking at a large change in a tiny fraction of the cross section.
10%? Are you sure?
Yeah, well, it depends which bin you say. Yeah,
5.2. I mean, in the
PP, take the PP as the vacuum. So it goes.
Oh, okay, PP. I'm looking at AA.
So Jamie, I'm looking at the upper left. I'm pointing to the PP and the upper left guy. It goes from 10 to the minus 2 to 10 to the minus 3 roughly. So it's an order of magnitude.
I know, but the AA is not.
We see it, we see it big.
So that's what I mean. So you because your distribution is flat for AA, so that means you would see some increase in the inclusive.
But they're also different populations. Very different populations.
Okay. That could be.
Different Quark-Gluon, different. Okay, but yes, absolutely, one should do apples with apples. It's a moving, yes. It's a moving target, but we'll get there. Okay, go
I
ahead.
mean,
Jamie.
so another comment. So although Peter said that he's very confident about background subtraction, suppose you have a little bit of background in your data, then the whole thing change.
Especially recoil for medium response.
Sorry?
But medium response can switch off background sometimes.
Oh, sure. So, James and Andrew, we did end checks so we're aware of this question. And if we've got it wrong, we're the first people who want to know that. So when actually, there's even a check in the paper about whether this effect is seen in the raw data before we do all of these corrections. And the shorter answer is indeed it did. Jamie, I don't know if you have a slide on that. That was kind of a complicated technical piece, but we go back to the raw data and say, can we see this before we do all the corrections? And indeed, the effect is there. Quantitatively, you have to do the corrections. But it's not that this was invented by the corrections. I think we've eliminated that.
And yeah, so the other kind of point about this is that a kind of full closure test was done with the corrections to kind of compare the what we'd expect from truth with no background to our kind of unfolded results. And this was done in quite some detail, and kind of the systematics associated with this were assessed in quite a lot of detail. So this is all kind of accounted for and included in the uncertainties there. Okay, and then just to kind of finish, I think answering Raymond's question. So so on this kind of recoil subtraction in Joule, I understood that these different methods shouldn't matter for these kind of observables that don't look at the jet substructure.
Jamie, we're a bit past the hour. Can you wrap up in 5?
Yes, yeah. So sorry, yeah.
Less than 5.
So I have a summary and then a couple of slides on an outlook, but I'll be quick. So to kind of summarize these measurements, I think bring a significant new insight into kind of jet quenching. So we've kind of mapped in detail kind of recoil jet modification over a range of PT. We've made the first measurement of jet azimuthal broadening, where the kind of R dependence of the broadening and kind of model comparisons as well indicate that the low PT broadening as well as the yield enhancement that we see is primarily due to the medium response to the jet. You can see this plus, so this is kind of sort of highlights from our papers. We also have many other interesting points in our papers, including kind of this delta recoil measurement in proton-proton collisions testing kind of PQCD predictions. The trigger track dependence of IAA, also the R dependence of delta recoil, and you can take a look at these papers for all of these measurements. So I have just a couple of slides on kind of the next steps. So we've measured this broadening. I think the next step here is to characterize the broadening and kind of understand if these are fully thermalized jets, whether there's a hard component. And to do this, the way to do this will be to study the substructure and fragmentation pattern of jets. So one example of some measurement that could go some way in answering this that we've been discussing is measuring the difference in jet axis definitions. So kind of the standard jet axis is determined as kind of a PT weighted sum of the constituent directions. we can take kind of the winner takes all axis in the jet recombination, which generally corresponds to the hardest constituent of the jet, and take the difference between these axes. This measurement was already done for inclusive jets by Alice for kind of narrow jets at higher PT. So I wanted to just show these really nice studies that were done by a master's student in Liverpool, Matt, where in these kind of broadening, in these regions where we see this significant broadening, this difference between jet axes is significantly broadened. So we get a significantly larger difference between these axis definitions if recoils are switched on in Joule. So this indicates that kind of the medium response significantly affects the jet axis definition exactly in this kind of broadened region, and we'll kind of add an additional way to constrain these broadening like effects. In terms of kind of measuring these sort of large angle scatterings, it seems that the way to go here is to look at jet substructure measurements, so to search for scatterings within the jets, and looking at kind of groomed observables where kind of the soft large angle radiation is removed to remove wake-like effects. So a nice measurement by Alice is looking at the hardest KT of subjets within a jet that Raymond and Peter have been working on, where I think the results here are perhaps not conclusive about kind of Moliere scattering, so there's no evidence that is found for Moliere scattering. CMS have made a nice measurement of the groomed jet radius and compared to these hybrid model comparisons as well, where we see for kind of the large groomed jet radius and a kind of agreement with the hybrid model with elastic scattering. So the picture is still kind of unclear here. There's indications that kind of photon jet correlated substructure is the way to go, which kind of removes a lot of uncertainties in the way jets are modified. Yeah, and we can we hope to have kind of more of these kind of measurements in run 3. Again, kind of pointing out that there's no model that describes all the data, and I think I mean I'm quite excited by these kind of global analyses, Bayesian analyses that are needed to kind of tune or exclude kind of jet quenching models, and this will be the next step.
Raymond, is that a new question, or your hand still up for the old question?
Oh, sorry, I don't know how that we missed that. Yeah, sorry, that was the old question.
Okay, and then to actually finish, yeah, Alice in run 3 and 4 looks like this. So there's been a significant upgrade program that really improves the kind of tracking resolution of the detector and also the readout capabilities, which will allow for kind of orders of magnitude data that we are taking at the moment. And yeah, at the end of last year, we had the highest energy lead run, where we collected 40 times more data in total than all previous runs. So yeah, we're kind of busy working on this data at the moment, and yeah, it's quite an exciting time to yeah, to be working on this, and yeah, we're hoping.
Yeah, Wrong has a question online. Go ahead, Wrong.
Hey, Jamie,
Hi.
this is
Hi,
a
Ramon.
great talk. So I'm still a bit puzzled why we don't see any enhancement in R equals 0.5, right? Because if you go back to your RAA as function PD for the R equals 0.4, you see the biggest enhancement at the first beam, which is 7 to 10 GeV, or right? So did you look at the data 5 for the 7 to 10? You showed 10 to 20. Have you looked at 7 to 10 where we see the biggest enhancement?
Yeah, so for the delta phi distribution, so this was kind of more challenging to sort of fully validate. So with the kind of the two-dimensional unfolding, there's kind of uncertainties associated with that. Yeah, we did take a look, but yeah, the results were kind of inconclusive to a precision where we would be able to say something there. So that's kind of why we stopped here. I think yeah, with more precise data, this I think would be interesting to check.
Yeah, because what I'm thinking is if this is from medium response, it has also shown up somewhere in your 0.2 and 0.5 results, right? I mean, for the 0.2, I would expect naively, I would expect you see lower at the lower PT, and 0.5 you see this enhancement at higher PT. For 0.2, can you push even lower? I know you did not, or you did not release, but internally, have you looked at for the 0.2 to even lower PT? Do you see enhancement?
Yeah, we looked at it, but yeah, I wouldn't be confident enough to make a statement on that.
Yeah, I think Ron's going after the point that everybody compares 0.4 and 0.5 comments on are the 0.4 point. This is what we also looked at. So somehow there's this market rise for the 0.4 not seen for the 0.5. If you toggle back and forth, the lowest bin for 0.4 is really quite high. 0.5 not so much. You know, they're the same data. What's going on?
Yeah, it's the same trigger selection, right?
Yeah, right. So in fact, they are consistent with the uncertainties. We looked in detail at that. It's, you know, you have to take the error bar seriously. Go back to the 0.5. Yeah, they are consistent. Your eye sees very different things, but if you look in detail and take the uncertainties seriously, they are consistent.
Yeah.
So,
But can I follow up on this? So that I see, but here now I'm a bit puzzled. So here, if you look at your RAA between 10 to 20, that's below 1. If you just look at central value, right? But if you later on,
we're losing our audience. Discussion is great. Let's thank Jaime, and then we can continue to discuss. Thank you.
Oh, okay.
Go ahead, Ron.
Oh, okay. Yes. So here your RA is less than 1 if I look at central value, but later on, if you look at your delta phi dependence, the RA is always larger than 1, right?
Yeah. So yeah.
If you go later, one of the
So
later the RA plot.
Yes. Yeah.
So here it's always larger than 1, right?
Yeah. So this
Why?
is a good point, and it's a point that we